Okay, so good morning, everyone. I will start making a recap of the last week. So first of all, we need to open the software, HEC-ResSim. I share my screen. Can you see my screen? So to open the model, we have downloaded a folder called HEC-ResSim 3.5. This is the last version of ResSim. It's different from the...
Your references, it is not, it takes time. Now your screen
it
is
takes time.
clear.
Okay.
Yeah.
Okay.
Okay, now your screen is coming.
Okay. The last version of ResSim is different from the previous one because it is a portable package, so you don't need to install on your computer. You just need to open the folder you download it from the HEC site and double click on resim.exe. And the software will open. So this is the user interface. Now we need to open the model. If you receive the folder I sent you, please you need to put it inside the shortcut we did last time. So you select one folder of your directories, and then you open from here, open watershed. I already have it, so this is the list of the shortcuts we did last time. You should have a shortcut called ResSim training, I think. If you click here, you can find all the model inside this shortcut. The model is called Atbara. So double click on Atbara, and then double click on the file called workshop. And this is the network. You can see from the module selector, you can choose between watershed setup, watershed network, and watershed simulation. Let's start from the setup. The first space in which we are working is the watershed setup. In this part of the model, we load the base map. To load the base map, we need to have the shapefile of our basin, and then we need to put the shapefile inside one folder, which is here. This is the folder of our model. The shapefile needs to be inside this folder, maps folder. Okay, so we copied all the shapefile here. Now we need to link the shapefile with the model. To link the shapefile, we go in View, in the View menu, Layers, and then load the shapefile from the Maps menu. Add map layer. This is linked to the folder maps by default. So here you choose just the file dot shp, the shapefile, not the other. You select it, and they are automatically loaded into the watershed setup. From here, we can decide to change the color, to make the labels, or to whatever we want. It's similar to the GIS. We can start building the model, the rivers and the elements of our network. The first thing to do is to make the stream alignment. So clicking on the stream alignment tool, we draw all the river from upstream to downstream, holding the control key down, for example, like that. The last point is before clicking the last point, we need to release the control key and then select the last point. This is how we draw the stream alignment. Inside the stream alignment, we can draw the elements of the model. In this case, we draw two kinds of elements, the reservoir and the diversion. We draw two reservoirs by clicking on the reservoir tool, and we draw the Tekeze Dam and the Umera Dam. Tekeze Dam is existing. Umera Dam is planned. When we draw a dam, we can say that this dam if this dam is existing or not by clicking on the dam, right-click, edit reservoir, and then we can say here in service, see, from which year it is in service, letting existing project checked. Umera Dam instead is not existing, so right-click, edit reservoir, we kit the existing project and let the year in service 1019. Okay. And then we drawn the diversion from one point upstream the Umera Dam. And we called it Umera diversion, Umera irrigation. Okay. This is the study configuration. In the study configuration, all the projects existing and planned are present. Then from the study configuration, we make other configuration. We made the existing and the planned configuration. To build one configuration, for example, the existing configuration, we go to the watershed menu and then configuration editor, and then configuration new. We put a name and a description that is optional. The description is optional. And then we need to choose which project we want to be inside the existing configuration. So we go to projects, edit project list, and then from that interface, we can add or remove projects or elements. Okay, in the existing configuration, we have the Tekeze Dam and the Umera irrigation diversion. And then we build also the future configuration. In the future configuration, we choose to put the Umera Dam and the Tekeze Dam without the diversion. The diversion is replaced by the dam. And okay. And for the watershed setup, it is all. Do you have some question about this part of the model? Did you get to open the model I sent you this morning, or do you work on your? Okay. So if there isn't a question, I will go on with the network. Okay, save our configuration and then go to the network, to the reservoir network. And then we need to open the network. This is empty. We just see the base map and the stream alignment, but this is empty. We need to open the network from the network menu, open, and open the existing configuration we did last time. If you want to build one network, it is from the network menu, network new, and then we need to put the name, choose a configuration. Okay, this is the existing reservoir network. I would like to change the color of the base map because I can't see the river. Now, inside the network configuration, when we build a network configuration, the HEC-ResSim import all the elements inside the network. All the elements we build in the watershed setup are imported inside the network, but we do not have the reaches. So the first thing to do is to draw the reaches using the reach tool. So we click on the reach tool, and then with the control key down, we click on the first upstream point. Then we release the control key and we click on the last downstream point. Reaches are the connection between the elements that are imported from the watershed setup. Then we need, inside the network configuration, we need to to describe the physical and operational characteristics of the elements of the control point, of the reaches, of the diversion, and of the reservoirs. So we started from the control point, the red dot here. Inside, click on one control point, Emba Madre, for example, and then click on Edit. In the junction editor, there is the first tab is info. In the info tab, there is the name of the river and the stream station, which are meters from the upstream point. And then we can choose if this point is a point of a local inflow. So this is a point of local inflow. So we put a name here, Emba Madre inflow, and a factor. This factor will be a multiplier of the boundary condition we are going to put inside the alternative menu. And then we can say also that this point is a point in which we check the data, a calibration point. If we have some observed value, this is the tab in which we can say we have observed value, and then we link the observed DSS inside the alternative. For this network, we have 4 points of local inflow. This with the white crown in the red dot. We have 4 points of observed value, but we of input flow, but we also have observed value. We have observed value here at HEC-Lab, and then at Enva Madre, observed, and then at CP7, which is Umera station, and I think in the last Wadi Lilium, and the last point. So this is for the control point. I think we did all we can. So let's go on to the reaches. Now we're going to say something about the reaches. So in the control point, we need to put the inflow and the observed flow, and that's all. Then let's go to the reaches. Let's select the one reaches and right click and edit reach properties. The thing we can say about the reaches is if there is routing and if there is losses and observed data. In this case, we don't need to do the routing inside. I think you will see on the HMS on the RAS training course. We need a lot of information to do this routing part. We choose null routing. In this case, it means that the inflow that comes from the upstream point will be transposed at the downstream point without any routing at the same time step. We can also choose to have losses in the river. If you know something about the losses, you can write it here. It can be constant or function of flow. And we can also have observed data. Okay. Save. Then we talked about the diversion. So right click on the diversion and open the diversion editor. Here we can, the diversion are a particular element in the ResSim because they have all the inflow that comes here in the upstream part of the element will go on the diversion. I will come back to the presentation. Reservoir. Eccolo qua. Diversion. Okay, the diversion have always priority. So all the flow that are coming from the upstream reaches go inside the diversion first of all, and then if there is some remaining flow, it goes through the reaches downstream. In the diversion editor tab, there are 4 tabs. The first one is the diversion tab, in which we say how much flow needs this diversion. We can choose between some methods. The simplest is the constant method, but we usually use a monthly varying method because diversion is used for irrigation or seasonal or monthly varying. So choosing the monthly varying diversion, we can choose a flow suitable for the irrigation project. And we put here inside the water requested by irrigation. In the following tab, we can choose if there is some routing. And let's keep the null routing. In the following tab, there are losses. In this case, the diversion is linked to a downstream control point. It means that some of the water we divert from the upstream point return in the river. We can choose how much of this flow come back to the river. It is the 15%, so 0.15. But we can also choose to have losses as a function of flow. In the next tab, we can say if we have some observed data. And okay, every time you see a star following in the network existing, it means that something has changed and you need to save the network. So you go to network save or file save watershed. It's the same. Can I go on with the reservoir? Okay. So select the reservoir tool on the left part of the screen, and then right-click on the reservoir and edit reservoir properties. Okay. The reservoir editor is more difficult than the diversion editor, because in the reservoir we need to know many more things. We need to know something about the physical data of the reservoir, and then we need to know how the reservoir works, the rules of the reservoir, and if we have some observed data to calibrate the functioning of the reservoir. The tab is divided into 2 parts. On the left part, we have the tree, in which we can select one element, and in the right part, we have the edit panel, in which we can see the data about the element we choose on the reservoir tree. The default element of one reservoir are the pool and the dam. The first 2 sign here. The other element are optional. We can add it, the other element. So let's come back to the model. In the pool edit, in the pool tab, we need to insert the pools, the pool curves, elevation storage area curves. So we need to have it with this unit of measurement and to copy it and paste it inside this tab. We can also add losses of the pool, and these losses can be through evaporation or through leakage. To add pools by evaporation, we right-click on the pool on the tree and add pool elevation, pool evaporation, or add pool seepage, the losses through the ground. We don't know, we don't have enough data to see if there are pool seepage, but we know that there is evaporation. So we choose add pool evaporation, and then this element will appear. If we click on evaporation, there is just one method, one available method. It is the monthly total evaporation in millimeters. So you can write the evaporation on this model. Here, when you see the negative evaporation, it means that on average, in July and August, the rain is more than the evaporation, so the evaporation is negative. So these are the information about the pool. And then we need to say something about the dam itself. By default, there is a dam at stream 0. In this tab, we can just add the elevation at the top of dam and the length at the top of dam. So the dam is functioning as a weir, which has an elevation of 1,145 meters above sea level and a length of 420 meters. But then inside this dam, we can add the outlet. We added 3 kinds of outlet. We added the power plant, the controlled outlet, that is mean as a controlled outlet for the irrigation, and an uncontrolled outlet that it is intended to work as a spillway for the floods. So let's start from the power plant and then go down to the uncontrolled outlet. In the power plant, there are a lot of tabs to be compiled, but not everyone should be are to be compiled. Surely we need to know a maximum capacity of the outlet, capacity in terms of flow. So for each elevation, we need to know how is the maximum capacity of each gate. We choose a number of gates and we choose the maximum capacity for each gate. This is compulsory. Another thing that is compulsory is the capacity in terms of megawatt. So we know that the Tekeze Dam is installed capacity of 300 megawatt. And then we also need to decide to write an efficiency of the turbines, which is 90%. Usually is about now 90%. These first three tabs are compulsory. The other are optional. Another thing that we need to say to the model is the tailwater. So to insert the tailwater, right-click on the power plant, add the tailwater elevation. In the tailwater tab, we just put the elevation of the tailwater. We can choose if it is a constant, or we can have a rating curve, or maybe also a DSS with some data that we are going later on to put inside as a boundary condition. We choose a constant elevation of 972. Then let's go to the controlled outlet, which is an outlet for the irrigation. Here we just need to put the number of the gates and the maximum capacity for each elevation. And then there is the uncontrolled outlet, which is the spillway. The spillway should have a minimum these three data: the crest elevation in meters above sea level, the wear coefficient, which is the coefficient of shape of the wear. Changing the wear coefficient will change the capacity of the spillway, and the length of the wear. The last thing about the physical data is here. Let's come back to the dam at stream 0. After that, we put all this data inside the outlets. We can see here a resume table in which for each elevation we have the maximum capacity passing through the controlled outlet, through the uncontrolled outlet, and the sum of the two. The controlled outlet, so it is the sum of the irrigation outlet and the power plant. The uncontrolled outlet is just the spillway. If we double click on the plot here, we can see the capacity versus the elevation. The total capacity is the red one. The spillway is the red one. It starts releasing flow when the elevation is 1140. So from this elevation, we have the contribute of the controlled and the uncontrolled outlets. For the physical data, we have said all. Then we go to the operation data. Okay, the operation data is the place in which we are going to say how the dam is functioning. Okay, in the ResSim, the reservoir works based on the concept of the guide curve. I will come back to the presentation, and here the guide curve. So the guide curve is the target level that we want the pool to be in for each month or day of the year. So if in this image here, for example, we want that in January, the pool level is at 480 meters. And then starting from May, we want that the level rises at 485 and so on. So the ResSim will work in that way. All the releases of the dam is choose to let the pool elevation be on the conservation guide curve. That is, if at the end of one particular time step, we have the pool level below the guide curve, then HEC-ResSim decide to close all the outlets to let the level rise up to the guide curve. Instead, if at the end of one time step we have the pool level above the guide curve, the HEC-ResSim will decide to open all the gates at their maximum capacity to empty the pool in order to come back to the guide curve level. This is the first choice the HEC-ResSim make to operate a dam. But we have also we can choose the priority of the outlet. I mean, we can choose if we prefer to satisfy the energy demand or the irrigation demand. Further, we can choose the priority. So the first thing to do in the dam editor tab is this. The first thing is to decide the levels. The conservation level, which is the guide curve, the flood control level, that is the zone up above the conservation, this zone here, and the inactive level. To do this, we go to Operation, New, and we build a new set that contains all this information. We build this operation set called base. Then we can choose the operation set from here. In the base operation set, we choose the conservation zone, the flood control zone, and the inactive zone, the levels. And then inside each zone, we need to decide one particular rule, or two or three. The rule we used is a rule for the irrigation demand and a rule from the energy demand. To build a rule, we can choose to build it from the tree here by right-click on the name of the zone and add the new rule, or also from here, rule new, from the menu. For example, if we want to add a new rule, we click on add new rule, choose a name, and then choose the part of the dam we want the rule operates from. It can be the power plant, the controlled outlet, or all the dam, and the type of the rule. In the energy demand rule, we put an energy demand for each month of the year, but we also make some we consider that during the night the energy demand is less than during the day, and during the weekend is less than during the working day. So from here, power generation pattern, we can choose the multiplying factor for each hour of the day and for each day of the week. So we put 0.2 for during the night as a multiplier, and 0.5 for the non-working days, which is these factors will be multiplied by the monthly total energy demand. Okay. Then we also add an irrigation demand, an irrigation requirement, which is function of date, and it has a limit type of minimum, and this is the water required for irrigation. We also add this minimum flow demand, which is the water needed downstream the dam. It is a limit type specified. It means that at least downstream the dam we will find this release from 10 to 50 cubic meters per second. And okay. Now, we have also observed data. Now we don't have any observed data for this dam, but if we add, for example, the elevation data, the pool elevation, we should click here on observed, but we don't have it. Okay, and then save. So in the network, in the reservoir network, we add the data for the control point. In the control point, we add the inflow and the observed flow. For the reaches, if we have some data about the routing and the observed data. And in the element, in this case, we have data for the diversion project, the water requirement, and we have the data for the dam. In the dam data, we need to know the physical data, the pool data, and the outlet data, and how it works, the dam. At least a first hypothetical idea of how it works, the dam, because then we can modify all these rules after we run the model to see how it works. Okay. We need to know another thing inside the network, inside the reservoir network, that is, we need to know the alternative. In the alternative, here on the menu, we decide the boundary condition. Okay, we decide the type step of the simulation, the initial condition here in the look back tab, and the boundary condition here in the time series tab. We also have the observed data here. It is a link with the observed data to make the calibration. All this data need to be linked to a DSS. For example, if I want to link the inflow at Burdana, I select the Burdana inflow and then select the DSS path, and the file is the DSS file should be here in the shared folder of the model. We will put the DSS file inside the folder called shared. See here. And then we linked all the DSS records to the point of the model. And close the alternative menu. Okay, so now we are ready to run the model. Can I run the model? Last week we arrived at this point. Okay. To run the model, we need to see, before running the model, we need to decide the period of the period we want to simulate. Okay. To run the model, we need to change the module. So first of all, we save the watershed, and then we choose the module simulation. That now it is empty. Okay. In this simulation model, in the simulation user interface, we have the map as in the display area as in the other modules. And then we add a new control panel on the right part of the screen in which we control the simulation. And then we have the menu almost as it is similar of the network module. Before let run the simulation, we need to know the period. Usually, to select the simulation period, we need to know the period of the input flow. In this case, the input goes from 1972 to 2023. So we have this for 50 years of inflows. But another thing we should control is the observed flow. For example, in this simulation, we have 4 observed flow, and the period in which the observed flow are better is from 1995 to 2004. But we can also run the simulation until 2023. Nothing will change. The simulation will work. So for this first model, let's choose a shorter simulation time from 1995 to 2004. Okay, so to create a simulation, now we can use the model. To create a simulation, we go to the simulation menu, and then we choose new, and then we give a name to the simulation. For example, sim existing. The description is optional. And then we need to choose the times of the simulation. There are 3 times because the start date is the date in which the simulation start showing us the result. So as a start date, we choose the 1st of January of 1995 at the time 0000. The look back date is a sort of warm-up of the model. We need a period of look back, warm-up, because we are dealing with reservoir, and a reservoir need times to fill or to empty. So for let's say normal reservoir, 1 year is necessary to warm up the model. For bigger reservoir, for example, a Swan Dam, also more than 1 year maybe is needed. You can try different data. In this case, let's save 1 year for the warm-up. So the look back date is the date that is before the start date, 1 year before in this case. We can choose it and we can change it after. And let's try with 1 year. At the same time, 0000. And then as an the end date, we choose the 1st of January of 2005 at the same time. The last thing is to choose the alternative. That is to choose the boundary condition and initial condition. And okay. So we have a simulation. We can run it. We go to the compute existing, and we wait. Okay, for the compute complete. This panel is very useful because not every time the simulation runs the first time. This is a simple network, so it ran the first in the first time, but sometimes it doesn't work. In this panel, there are the message outputs. You can see here the error you made or where you need to change something. Okay, we have the simulation done. Now we are going to check the result. Okay, there are different ways to check the result. The first is, for example, to look at the flow at some control point. So let's click, for example, on HEC-La or Hembra Madre. Let's click on HEC-La, right click and plot. Here you can see a plot. The green line is the computed flow. The red line is the observed flow. They are very different because the HEC dam it is supposed to start at 2009 after the 2001, 2002. So what we're seeing here is a flow that is coming out from the dam, which in the reality is not. You can see a black dotted line here. This is the line in which the simulation starts. Before this line, there is the look back period, the warm-up period, and then there is the simulation. You cannot see the result before the look back period. Okay, let's close this plot. And then there is the result on the reservoir. Okay, so click on the reservoir, right click, and then the plot. Okay, and then you will see this kind of plot. In the upper plot, you can see the level of the reservoir, the elevation of the reservoir. In the purple lines are the reservoir zone, the flood control, the guide curve, and the inactive zone. The red line is the computed levels. Green line is the computed levels. In the lower part of the plot, we can see information about the flow of the reservoir. The black line are the inflows. The green line are the outflows. from this plot, we can already see that there are some problems. For example, if you zoom on 1996, we can see that there is an overtopping of the dam. We should avoid the overtopping of the dam. So later on, we will try to modify the guide curve in order to avoid the overtopping. Okay, another very useful plot is the plot releases. Right click on the dam and plot releases. And here there is a plot with many different color lines. The red one, zoom on 1 year, for example, on 1996, in the year that give us some problems for the overtopping. The red line is the outflow from the power plant. You can see that until July, there are no problems. From the power plant release what is requested. Starting from August, the power plant release at the top of its capacity. When the red line is at 220 cubic meters per second. And then there is the irrigation outlet, that is the green line. The same thing until July, there is no problem. And from the irrigation outlet, the flow is what requested. From August on, the irrigation outlet release at its maximum capacity. And then there is the yellow line, that there is the spillway, the release from the spillway crest, which depends just on the elevation, because it is an uncontrolled wave. And then the blue line is the overtopping from the dam crest. It means that the elevation of the dam is above the top crest of the dam. And so there is an overtopping of the dam. So we will need to do something to avoid the overtopping. For example, to save, we will try to save space before the arrival of the flood, to store the flood, modifying the guide curve, but this after. First, I want to show you another thing, another method to check the result, which is this, the decision report. So from the dam, right click on the dam and release decision report, the last voice. It is a huge table. Let's go on 21 of August 1996, which is the date in which the overtopping started. '21 of August, here, 1993. Okay, you can see here that the first column is the elevation. The elevation is above the crest of the dam. Okay, above top zone. It is written above top zone. This is so the first column is the current pool level. Active zone is above the top zone. Okay. In the second column, we can see the inflow of the dam for 1,000 cubic meters per second in that particular time step. And then the following column are the release from each outlet. Okay, in the fourth column, which is called dam at stream 0, shows the sum of all the outlets of the dam. So in this time step, for the dam, and just 1,500 is flowing out the dam. This is the sum of all the outflow, of all the outlet. And then in the following column, we can see the uncontrolled flow. So from the uncontrolled flow at the dam, which means from the crest of the dam, it is flowing out 139 cubic meters per second. And then from the irrigation control outlet is flowing out 880 cubic meters per second, from the spillway 500, and so on. So we first of all, we see the sum of all the uncontrolled, of all the controlled and uncontrolled outlet. And then we see the overtopping, the irrigation outlet, the spillway outlet, and the power plant outlet. It is very useful to see how the HEC-ResSim works. Okay. So now we want to calibrate, let's say, calibrate the model, because it's a particular kind of calibration. So we run the model. We see that there is one big problem here. We need to solve this problem. There can be many type of problems in the dam during the dam life. This is one kind of problem, which is one flood. But there is also can be a problem of shortage. So we will try to make these two kind of problem, the flood and the shortage. Let's see first of all the flood. Okay. To solve the flood, we need to change something in the network. We need to calibrate the model in order to optimize the dam, the functions of the dam. We cannot calibrate the dam in a proper sense of the word, because we don't have any observed data starting from 2009 when the dam was built. So we cannot make a calibration on the observed value. If we have observed value, we can do a calibration, but not in this particular case. So The calibration here is intended to find an optimal way from the dam to work. Find a way, find some rules, some guide curve to avoid problems, avoid overtopping, avoid irrigation and power shortages. Okay, in this case, we need to solve this problem. We have an overtopping, a flood. We need to save space inside the dam to store the inflow coming from the upstream part of the dam. Let's open the plot of the dam. So right-click on the dam and plot, and keep open this plot, and zoom on 1996, 1997, for example. We can see that for every year there is the black line is the inflow of the dam, and the green line is the outflow. We can see that all the inflow coming during spring, from April, May to the first summer, from May to June or July, is stored by the dam. Okay, so we need to release this water in order to have more space to store than the flood that is coming usually during the late summer. Sorry. Also in 1997, we have the same problem. We store too much water and we need to release it. So we would work on the guide curve. We will lower the guide curve in order to release the water that is incoming during June and July. We can modify the dam from the simulation module. So right-click on the dam, edit reservoir properties, and we have the same reservoir editor as we saw in the network module. It is the same. From here, we can modify the operation of the reservoir. We can modify the conservation zone. Let's try with this guide curve. You can see it from here. I will change it. Okay. I will change. Yeah. So from the 1st of January, it is no more 1,140, but 1,130. And then on the 1st of August, the same, 1,130. And then there is a peak in the 1st of November. The 1st of November. Okay, if we apply our changes, we can see that the dam, the plot is changed. It's changed. Now we have lowered the guide curve during the first summer and during the spring. The flood in this particular place start during the late summer. So in this period, the dam is allowed to raise the level. From August, the dam can raise the level. Okay. Apply and okay. And then save file, save watershed. Because I saw the star here, so save the project. Okay, and then we can run the model again. We run the model again, so compute existing. Okay. And then we check the result. So we need to check the plot to see if there is again an overtopping of the dam. So right click, plot, and let's see on 1996 if there is again an overtopping. It seems no, almost, but no. The level is inside the flood zone. So it is released in a normal way by the spillway, by the irrigation and the power plant outlets. So let's check because we lowered the guide curve. It means that the pool level is lower than before. But we need to check if with this lower level the irrigation, the power demand is met, because lowering the level of the dam, it means that we produce less energy, because the energy produced depends on the difference between the current level and the tailwater level. So let's check the energy production. To check the energy production, again, right click on the reservoir, plot releases. Let's zoom on the year 1996, and the green line is the power plant releases. It seems that there is no problem. There are no shortages of energy supply. In August, the level of the reservoir raised the spillway level, so the spillway will work. In this year will work. This is the only year that the spillway work in our simulation. Okay. We can save this configuration because we changed the reservoir inside the simulation module, but we didn't change the reservoir inside the network module. If we come back to the network module, we will see the reservoir as we did before, with the guide curve all at the same level all along the year. So HEC-ResSim has a very useful tool, which is this. We can modify the network from the simulation module, but then we can apply our changes to the network module. And it is made by like that. So you right click on the simulation, on the control panel, on the simulation you just make, and then save to base directory. If you click on save to base directory, you are and then select the network existing, you are going to save the change you made on the simulation module to the network module. But there is another useful tool, which is the replace from base directory, meaning that maybe you were wrong changing the guide curve. You want to come back to the initial condition of the reservoir. You can do it by replace from base directory by this tool. Right click on the simulation and replace from base directory. So the two modules, the reservoir network and the simulation module, are linked by this tool. Save to base directory is from the simulation to the network module. Replace from base directory is from the network module to the simulation module. The last things we need to check on the simulation module is the report. So you go to report menu, and then, for example, power summary is very useful, because from here you can see on average for every dam you have in the model. We have just one dam, so we can say on average which is the energy generated per time step on average, on a maximum, and on a minimum. And then the power generated, average, maximum, and minimum, the plant factor, the flow passing through the gates, and so on. There are also other kind of reports. For example, the first one, reports, reservoir summary. For each dam, we can see the average volume, the average elevation, and the average or maximum or minimum release from the controlled and the uncontrolled spillway. And there are many other type of summary you can control. Okay, save the watershed. And now maybe here now, if you want, or later on, we will try to make some exercise with this network. We will try to double the energy production to see if doubling the energy production, we can also have the irrigation requirement as before. Okay, we can meet the irrigation needs, and we will try to do to double the irrigation need without affecting the energy production. We will try to add a rule to have a minimum flow of 200 cubic meters per second at the downstream point. But I would like also to add another exercise, which is this. We will try to create a energy shortage. To do this, we need to lower the inflow, the boundary condition of the model. So we will try to halve the inflow of the model. Inflow. Right, to see if we can produce energy or irrigation, or we can meet the irrigation demand. So we are going to work on this simulation on this network, existing network, and try to do these 4 things. And then we also need to create a future network. But let's start with this. Before doing this exercise, before we start doing this exercise, do you need some clarification? Do you have some doubt? So the pause will be at 11, not 1. So we have another 20 minutes. We can try to do the first exercise. The first exercise is double the energy production. We are working with the new guide curve. Let's keep it as it is. In this pool configuration, we try to double the energy production, the energy demand. We double the energy demand. So we go to this rule, HP demand, and we just select the energy requirement, right click and select fill. And we will use a multiple factor of 2. Okay. And then apply and okay. And then we just run save, simulation save, or file save watershed, it's the same. And then we run the simulation to see what happened. So to see what happened, we double click, we right click on the dam and the plot releases. Something happened. Something happened. The outflow from the power plant is the green one. So let's check the same year, 1996. It seems that it's the water demand, the energy demand is almost always met, apart from this short period here, the first days of June. And also in 1997, there is a big shortage of water and of energy, of course, and also of irrigation. So the answer is no, we cannot double the energy demand of the network. Let's see what happens on the dam. So you can keep this plot open and then right click on the dam and plot to see, for example, what happens on 1997 when there is this big shortage of water from April to June. No, 1997. In fact, the water of the dam lower down to the inactive zone. When the level of the dam is on the inactive zone, all the outlets are closed. Even if they have priority, they are closed because it is not allowed that in the inactive zone, it is not allowed some water will come out from the system, from the reservoir. So from June to from April to June, all the outlets are closed, and there is no energy demand, no irrigation demand. There is anything. So we cannot double the energy demand. We come back to the first energy demand we had. To do this, we right-click on the simulation in the simulation control panel, and then replace from base directory. In this way, we have the initial condition of the reservoir, and then compute again to come back on the initial condition. Let's check. Okay. Maybe you can try with another multiplying factor. We use 2 as a multiplying factor, but we can use also 1.5, 1.2 to see what is the limit of the reservoir. Another exercise we want to do is this. I want to double the irrigation demand and check if the energy production is met. So to double the irrigation demand, we need to open the editor of the reservoir. So right-click on the reservoir, edit reservoir properties, and then we go to the operation tab and to the irrigation rule. Let's double the water requirement as before. Select the flows, right-click, fill, and multiple factor 2. Okay. Apply, okay, and then save. Save. And then compute. When the compute is complete, close the window and check the releases. Check plot releases. So right-click, plot releases, and let's zoom on these 2 years, 1996, 1997. I think we have the same problem of before. When we doubled the energy demand, there was a shortage in the same period here. And now again, we have the same problem. So it is not possible to double the irrigation demand as before. We need to come back to the previous configuration. Let's check also the plot, the general plot of the dam. So right-click on the dam plot. Let's check the same years, 1996 and 1997. There we are. We have the same problem. From April to June, we raise the inactive zone, and so all the outflows are closed. All the outlets are closed. We can maybe we can modify again the guide curve in order to store more water. For example, during July or August, we can modify a little bit the guide curve. There are many possibilities. So for now, I will come back to the initial condition of the reservoir. So let's close all this plot. And then right-click on the simulation, replace from base directory. In that way, we have the previous water requirement, the previous rule. Okay. There are some doubt. Can I go on? Okay. Let's try the exercise 3. We want to add a rule to have a minimum flow of 200 cubic meters per second at the downstream point Emba Madre. Okay, let's try. Let's start trying, and then maybe we will finish it later. So we need to add a rule because we want that here in Emba Madre, we want to have always a minimum flow of 200 cubic meters per second. In Emba Madre, there are some inflows which are let's zoom on one here. In Emba Madre, we have, I will hide the observed flow for one moment. So right click, if you want to hide some line, you right click on the line you want to hide and then hide curve. This is I'm hiding the observed curve. I have two lines, two green lines. This one is the inflow coming from the HMS model. It is the local inflow coming from this point, from the basin. And then there is another input in Emba Madre, which is the inflow coming from the river that is from the dam. Okay, so this one with this little triangle is the local inflow. And this one, the green line without triangle, is the flow, is the flow from the Tekeze dam. So in Emba Madre, we have the sum of these two inflow. I want that for every time step of the simulation, I want here to have a minimum flow of 200 cubic meters per second. I don't know if it is possible. We can try to do it. Maybe for navigation, for other purposes. We can try to see if it is possible. It seems no, because we have some shortages during the summer, the first during spring and the first summer. Let's try. We need a new rule. Okay, so what we're going to do is this: open the editor of the reservoir, and we need to add a rule. Before adding a rule, I want to to make this rule minimum flow inactive. So I just select the rule and then right click and then remove rule, because I don't need it a minimum flow just downstream the dam, because I'm adding a new rule which is a minimum flow in a control point downstream this point. So I need a new rule. In the conservation zone, right click and add a new rule. Let's call this rule EMBA madre minimum. EMBA madre minimum. The release is from the HEC dam. We cannot choose, in this case, we cannot choose from which of the outlets we want the flow pass through. It is, we must choose between HEC dam or HEC dam at stream 0. And then it is a special kind of release function. It is a downstream control function. So select the downstream control function. And then we must select the downstream location, which is EMBA madre, the control point EMBA madre. And then OK. See, we have this new symbol here with a house and a flood. In the last version of the model, then the point is became gray. In this version, it seems not. Now we need to say that we want a minimum flow of 200 cubic meters per second. So it is a function of date. It means that every time I want this kind of this particular flow of 200 cubic meters per second, but I can also choose that maybe in summer I want more and in winter less. I want always 200 cubic meters per second as a minimum. So in the limit time, I will put minimum. And that's it. I can also choose if I want to have some hour day multiplier, as we did for the power requirement. But I think that this is all. So apply. Let's add the same rule also in the flood control. So right click on the flood control, use existing rule, and choose EMBA madre minimum. We can also choose to prioritize this rule. Let's say that I want this to be the first rule that the reservoir is obliged to serve. So right click on the rule and move to top. Also in the control, the flood control, right click, move to top, apply, and OK, and save. Simulation, save. Okay, see that the EMBA madre control point now is inside one gray square. This is a control point. Okay, I want to remember that I'm not changing the network module. In the network module, this rule doesn't exist. Okay, it exists just in the simulation module. If it works, I can choose to save it in the network module by using the same tool, right-click, save to base directory. Let's try what happens. So compute, and let's try. Okay. Close. Let's see on EMBA model, first of all, if it is if this rule is met. Plot. I think yes, it is met, because we have always let's hide the observed flow as before. Right click, hide curve, and zoom on these 2 years. Of course, the local inflow is the same as before because we cannot change the input of the model, but we can change the rules of the dam. In fact, the dam release always 200 cubic meters per second. I don't know if it is releasing this flow from the PowerPoint, from the irrigation, from the power plant, from the irrigation outlet. Let's check. It works on EMBA model. I don't know if it works for our irrigation purposes or for our energy demand purposes. Maybe we will check it later, just see the plot releases, and then we will discuss it later. Let's zoom always on these 2 years. It seems that it works. I don't see any power shortage or irrigation shortage. We need to check on every year, maybe here. Okay, this during the descending line of the flood. Maybe here during autumn. Okay, let's after the lunch we will check the other plot. Okay. Do you have some question? No, so we see you on at 2 p.m. If there isn't any question, I close the call and see you at 2. Thank you to you.
Thank you.
See you later. Goodbye.